missing anybody today? Nope, okay. Last period. Okay, now, it says when t equals 0, the particles and x equals -1. How would I write that in math symbol notation? How would I write that? In function notation. Now, since it's a particle moving on the x-axis, typically its position we call x. So let's use that. So say it again. X of 0 equals -1. When t is 0, the particle has a position on the x-coordinate of -1. That's how that would be written. All right, in part A, you're supposed to write an expression for the position function at time t. Now, those of you that had time to work on this problem, and it's a calculator problem, probably the first thing you did was what? Tried to do the antiderivative on your calculator, right? And what happened? Doesn't do it. There is no antiderivative that we can write as a formula. So, what might we try next? Now, when we say we want the position function, what we want is x of t. So what do? Write it as an integral. Now, we haven't done a lot of those, or we haven't done them for a while, and when I graded AP tests a couple years ago, that was one of the free response questions. That was a big part of one of the free response questions, and people kind of struggled on that. There were a lot of different places people messed up, including not even knowing that they were supposed to write as an integral. That is a common question. When you have to do an antiderivative, but there is no antiderivative, write it as an integral. So let's talk about the various parts of that. So we would have an integral from what to what? Could be 0, probably not though, unless, well, we'll see. I'm going to actually leave that blank for a minute. So, something to what? T is the key. T has to go there. This variable here, the input, has to match that. Now, what would go inside here then? No. Something other than t, right? But it has to be this function, but it can't be in terms of t. So you actually could just write v of x here, dx. Or you could go square root of x times cosine of x dx. Now, we're not quite there yet because we don't have this. Now, if you remember, the left endpoint is what was the plus c part. Well, that means this initial condition's got to be involved somehow. So, how could we do that? Now, what you guys were saying 0 down here. Let me, see, this is a little more difficult because of this initial condition. Let's pretend the initial condition was this. X of 3 equals 0. Now what would go right here? 3. Because then x of 3 would be the integral from 3 to 3, which of course we know is 0. But since they have it equaling -1, that causes a problem. Or makes it more difficult. Okay? So any idea? Now, so you guys said 0. So let's say you did put a 0 here. Because there's a 0 there. Now if you put a 0 in for t, you get the integral from 0 to 0, which should equal 0, but it equals -1.
Why did -1 plus the integral?
So or just go integral -1. Same thing. That's right. That's a nice adjustment to make right there. And you could, or you could do -1 plus the integral. Okay? Because that would be like its starting point, right? It's kind of like that position. Where did it start? And then its position after that. So doing -1 plus the integral, or do that. Now there would be another way to do it is you could say, okay, I don't know what this is, call it A. But when I put in a 0 right here, I know I have to get -1. Right? I don't know what the left endpoint is, but I know when I put in a 0, I've got to get -1. And you could do a solve on your calculator. You can actually do a solve, type that in, and tell it to solve for A. That comes out to like 6 point something. So then you could have just the integral from 6 point something to there. But this would be okay. This would be acceptable. And I like it. That's a good way to do it. Okay? All right. So I wanted to discuss that just a little bit because that's not something we've seen a lot of, and it is something that I've seen be on the AP test quite consistently. So I wanted to look at that. All right, now let's come back and do sample 3. And I'd like for you to look at problem number 26. Problem number 26 on sample 3 is one that we still can't do. It says the base of the solid is a region in the first quadrant bounded by this line and the coordinate axes. What's the volume of the solid if every cross-section perpendicular to x-axis is a semicircle? Now, what we learned yesterday is we can find the volume of a solid by slicing it and letting the integral add up the slices. Well, what they're telling you here is the slices are semicircles. The slices are semicircles. So we want to set up an integral that will add up a bunch of semicircles. That's next week. Okay? So you still would skip this one. The word that's missing here, which is the ones we learned yesterday, is what? Starts with an R. Revolving. Rotating. The ones we're doing are solids that are revolved around an axis. So go to the calculator section and problem number 30. Okay? Revolving or rotating. So if we go to problem 30, this is also one that we skipped. The region in the first quadrant enclosed by the x-axis, the line x equals pi, the curve y equals cosine of x, is rotated about the x-axis. What is the volume of the solid? So, Brittany and everybody else on your calculators, okay, go in the graph screen and graph cosine of x. Let's do our window settings from 0 to pi because that was the vertical line. X equals pi was one of our boundaries. Yeah, let's do a zoom fit. That's good. Now, on this particular one, when we do a zoom fit, I don't like the fact that I can't see the x-axis. So go into your window settings, and I would change my Y minimum to something a little bit negative, like -0.1 maybe in this case, because the Y values are so small. I might set my Y min to -0.1 just so I could see my x-axis. All right? So, x equals pi is somewhere over here. Okay? So we've got this region in here that we're going to revolve. There's a strip. I don't know if I can draw. Let me see how this works. Seemed to me I tried this before. It wouldn't let me draw over top of this. Yeah. Okay, I've got a strip right here. Now, for those of you that were gone yesterday, what we said was we're looking at this region here, right here like this. We're going to revolve that around the x-axis. That's going to create a mirror image of that solid here. That's kind of hard to see. And it's this strip right here represents, here would be a slice out of that solid that would be a circle. Now what we did, which you guys missed yesterday, is the lemon. We've got the solid. Oh, you were going to take this one. You still want it? This lemon with the smiley face. So if we slice this lemon, okay, into, we did yesterday 6 slices, okay, and add up the volume of each slice, use the integral to add up the volume of each slice. Well, each slice is going to be a circle. Okay, so it's going to be a cylinder with a thickness. Now, if we did it in 1,000,000 slices, they'd be paper thin. So what we said yesterday is to find the volume of a solid, we do the integral of the area of a slice times the thickness of the slice, which would be the dx, right? Really narrow. And area times thickness, that would give us volume. Okay? So the area of a slice, of course, is pi times the radius squared. Now, if we look at one slice, that circle right there, we look at one slice, that strip right there is the radius of that circle. That strip is the radius of that circle. Now, what would be the length of that strip? I'm going to call it r of x. What would be the length of this strip? This y value, which is what? What's this y value? Cosine x minus this y value, which is 0. And anywhere I move that slice, that strip is going to be the radius of that slice. Okay? So my integral will be from, and this is pi over here, so my strips fill the space from 0 to pi. My integral will be the area of the circle, which the area of a circle is pi times the radius, and we just said the radius is this, squared, times the thickness of the slice. Pi times radius squared is the area of a circle. So go ahead and type that into your calculators. Okay, so the integral is adding up all those circular slices from 0 to pi. I'll have to be careful with the squared. I think, oh, that's right. That square's right. She put another parenthesis. Okay, good. So there it is, 6.040, which was what, C? C. Okay? So there you go. So the thing we learned yesterday, that's what that would look like. Okay? Now if we back up, again, just to remind everybody, but also to help those people that were gone yesterday, here's another problem with the region. We're going to revolve around the x-axis. If we revolve that region, we create a solid. So here you can actually see a solid being revolved. What we did yesterday was we took a picture of half the lemon, which I'm going to show you in a minute, and we imagined that being revolved to create the lemon. But here's your slice as a circle, and the integral is going to add up all of those slices. And that's what this does over here. This adds up the volume of all the slices. And of course, we really use area as our formula because the thickness is the dx. Okay. Now, one last thing to the calculator. I thought this was so cool once I kind of figured it out yesterday. I wanted everybody to get a chance to do it. So, and you could try this on your calculator as well. Somebody have their lemon packet real handy with numbers written in that front page? A little bit handy. Okay. So everybody on your calculator, and Brittany, do this. Go to the document button, the doc button, and do File, New Document. Do you want to save, unsave? Say no. Okay, and add a list and spreadsheet. Now this is what I did yesterday. Okay, now arrow up to next to the A. This just gives you a title for this column, and type X1. Okay, you can give it a name, better name if you want. You hit enter, go over to the right by the B, put Y1. Okay, this is so much. I was trying to make it difficult. I was going to have you guys do it, but I wasn't sure how long it would take, and I hadn't done it really with these calculators yet. And it's so much easier than our old calculators. It's crazy. So I wanted you to get a try. So if you arrow down in that gray box, that's where you could put a formula, like on a spreadsheet. You can put a formula in there to generate the cells. And then arrow down, And now let's type in, okay, put in a 0, and then go down, 1.1, and go down, 2.2, 3.3, 4.4, 5.5, and 6.6. Now, if you guys were gone yesterday, what we're doing is they measured across the lemon, and they divided it up into 6 equal segments, and it was 6.6 centimeters, and so that's 1.1 for each width. Okay, now arrow up to the top again, and the Y column, one more. There you go. And in the Y column, next to the 0, we'll put a 2, and then go down to 2.3. No, oops, I'm sorry. The first one should be 1. First one should be 1. Then go down, and then do 2, and then 2.3, and then 2.2, 2.1, 1.5, and 0. Okay, now, what we want to do is, and then those were the heights of the lemon from the middle. So what they did is they set the lemon, they put an x-axis right through the middle, and they measured the heights, okay? But then we wanted to draw a graph of that. So go to the document button and go to, I don't know what, page layout? No. Insert. There we go. Insert a data and statistics page. We could have went control document just to add a new page real quick. But what this does is adds a new page. Now look, there's those dots. Now, notice over here it says click to add variable, and down here if we arrow, move your arrow down here on the bottom, it's just randomly plotting them. But if you arrow down, okay, if you arrow down here till this comes up, it says click to enter variable. We'll go ahead and click. And there's your x1 and y1. Well, down on the x-axis, we want our x1. So go ahead and choose x1. Watch what happens. I just think this is neat. I'll just kind of go down it. Now, if you look, you got 0, 1.1, 2.2, 3.3, 4.4. But it's just plotting the x, okay? But now over here on your y, so if you arrow over, and then once you get there, it kind of highlights and it'll hit enter. And y1, and watch this. Okay? So it's really neat. It's much more interactive than the old calculators were by far. So what this is a picture of the sketching of the top half of their lemon. It's not symmetric. You know, this one's actually pretty symmetric, but some lemons really weren't. Then, of course, what we wanted to do was fit an equation to this. And it's not symmetric, so a sine doesn't work very good. A parabola wouldn't fit real well. But it turns out a fourth degree is not, it doesn't have to be as symmetric either. And so we did a fourth degree. So what you want to do now is you go to your menu, and you go to Analyze, down to Regression. This is called a regression analysis. And this is some serious high-powered mathematics this thing does in a pretty short time. And go down to Show Quartic. Quartic is a fourth degree equation. And just that fast, it finds, based on those 6 points, a fourth degree equation that fits that. Now, the coefficient on the fourth power is pretty small, almost 0, which means a cubic probably could have fit it pretty well too. But anyway, so that's the equation for the top half of the lemon, and then of course we went on and used that and did some things. But I just thought that was kind of neat. And then one thing I found out yesterday when I started doing this is when you go back to the previous page and you change those numbers, it automatically updates your graph and your equation as you do that, which is really cool compared to what the old calculator used to do. All right, so I wanted you to see that. All right. Let's take a look at number 9 in your homework. Okay? You guys that were gone, that LH packet I handed out the other day. Okay? That's one other packet you have to get out now. The homework packet, the LH packet. Okay, we had 1, 2, 4, 9, and 10. Okay, page 419. So the first line, page 419, the first page 419 line, please. Okay, we had problem number 9. Now, problem number 9 had this picture. Okay? You were supposed to take the region bounded by y equals x squared. Now today we're going to work a lot on defining the correct regions. Y equals 4, and it was in the first quadrant. That's how that one would have been given to you. Okay? So it was this region here. And you were supposed to revolve that around what? The y-axis. Okay? So we're supposed to revolve this around the y-axis. Now, if you're going to revolve that around the y-axis, that's going to take a strip that is horizontal. So like we said, you've got this strip, you revolve it around the y-axis like this, it creates a circle as you rotate it around. The slice will be a circle. Now the other half will be here. It'll be this kind of a thing like so. There's your slice. You don't need to draw that in, but there it is. This strip is the radius. So the radius, and I would write that as r of y. R of y. Now that's the same as x, okay? But the length of this strip is the right x coordinate. Now what's the right x coordinate? What's the right x coordinate here? X equals square root of y. The same thing we did last week. When you have a horizontal strip, you've got to solve it, okay, for either the x or the y. We want the right x coordinate, which is square root of y, minus the left x coordinate, which is 0. That is going to be the radius of that circular slice. Okay, the area of the slice, since it's a circle, is pi times the radius squared, times the thickness. Area times thickness makes volume. And the integral goes from 0 to 4. Again, just like last week, the strip fills the space from 0 to 4. Because this up here is the point 24. This up here is the point 24. So you type that all in and you get what for your answer? 8 pi. Right? Now, I want you to consider this. On your scratch paper, in your notes, whatever. I want you to consider this region y equals x minus 3 squared. Let's say you were given this problem just like this. Take the region y equals x minus 3 squared, bounded by this, and revolve it about x equals 3. Okay, so draw me a sketch of that region, and then we're going to talk about it. Now, you will get to use your calculators. Hopefully, you don't need them for a problem like this. There may come a time, which would be in your packets or on your test, where this would be a no calculator problem right here. Okay? Now, what's trickier about this one? It's not revolved around one of the axes, X or Y axis. What else? Yeah, if you put in x equals 3, and you revolve around you revolve around that line, what happens? It overlaps itself. It revolves onto itself. So the solid wouldn't change, right? The volume wouldn't change. So in reality, if I had a problem like this, I would just revolve this region. I would just pick one of the two regions to revolve. Because if you revolve the whole region, it really doesn't matter. It's not going to change the answer. So to make it easier, it's probably best to do this. Now, which way is this strip going to go? Horizontal or vertical? Horizontal. Again, because we've got the axis of revolution here, and the strip has to be perpendicular to that, right? It has to rotate like this to create the circle. So it's going to look very much the same. Matter of fact, isn't it the same exact volume? Isn't it the same picture? I mean, it's a different picture, but it's the same volume. It just shifted over, isn't it? So, but it's going to look different when we initially set it up. And we're going to get into some more of these today, so I thought this would be a good one to start with. So this is still your radius, right? Here's going to be your slice, like so. It's a circle. The integral's still going to go from 0 to 4. It's going to be pi times your radius. Our radius is still this x-coordinate. Now, what's that x-coordinate? We got to take this equation and solve it. So we get square root of y equals x minus 3, be positive square root because it's the right half, and then add 3. So square root of y plus 3 is equal to x. So the right x-coordinate is square root of y plus 3 minus the left x-coordinate, which is 3. Right? It's right minus left. So the 3's cancel out. So when you go to do pi times your radius squared, look what happens. You end up with the same exact equation as you did over here. So, of course, it's the same volume, so that's good. So it should be. Okay? All right. Now, let's do this one. Let's repeat number 9, but let's revolve about... No. Revolve about y. No. X equals 2. Let's do the same thing. Wake up research paper boy here because he's going to want to see this. Okay? So, we got... Okay, so let's do the same region as number 9. You were doing okay until you started snoring. Then we had to do something about it. All right. Okay, so go ahead and draw. Go ahead and draw the picture. Go ahead and draw the picture. Okay. But we're going to revolve it about the line x equals 2 this time. Same picture as number 9. This isn't very good. I haven't done many of these with this tablet. I'm not very good with this. Okay, so here's the point 2,4. Here's the region we want to revolve. Now, what's going to be different here?
One side of the axis is revolution.
What do you mean now? Say it again. We're going to revolve it around this line. We're going to take that region and revolve it around. Well, you could, but finding the piece that's missing isn't any easier than finding, well, I guess it might be a little bit.
Yeah, you just straight up like.
Well, first of all, can you picture what this thing looks like? I mean, it's going to be, it's the other half's going to be over here, right? Like so. So it's going to be this kind of this, where this kind of goes, whoops. Like that. Right? And forget that little piece there. Right? And that's going to be empty in there. Now, but again, like we said yesterday, we're not trying to find the volume of that empty space. We're trying to find the volume of the solid part, the shaded part, right? Now, I guess what David is saying is it's a cylinder, right, because of this straight side here. And then you could do the volume of this by doing a right minus left, putting a strip in there. And you could do that. Now, it's not always going to work that easily. So I would just, in general, I would rather just try to do this. What are the slices going to look like? See, if you slice this, aren't you going to have that donut that we talked about yesterday? That washer shape instead of a circular shape? Okay, now it's still circular, but what is, and if you go back to our formula over here on the board, the volume is the area of a slice. Well, so far our slices have always been circles, right? Our slices have all been solid circles. Right? Well, now we've got a slice that's a ring. Well, how do you do the area of a ring? Yeah, big area minus little area. Now, the way I'm going to suggest we do it is to factor out the pi, just so we don't mess up the subtraction part or forget about it, is if we factor out the pi and we can actually pull that out in front of the integral. We could have been doing that on these other ones as well, pulling the pi out in front. This is how you do the area of a ring. Now, I want you to look at something here. In this ring, here's the outer radius, and here's the inner radius, right? Where does a strip come into play? When we draw this strip right here, is that the outer radius or the inner radius? It isn't either one. It's the outer radius minus the inner radius, which we don't even want that. So the strip, now, so here's something different. This would be the first time that the actual strip length doesn't really matter, or at least this strip doesn't really matter. The strips we want are these strips. There's your outer radius right there, and there's your inner radius right there. This strip doesn't matter. Now, it's still a right minus left and a top minus bottom kind of scenario. In this case, right minus left. And it's still the strip length, but it's a different strip than what we're, because where's a radius always have to come from? The center. The radius always has to come from the center. And the center is your axis of revolution. Okay? All right. So let's go ahead and to really become important to write this stuff out, I think. This is going to be a horizontal strip, so it's still going to be in terms of y. So what is your outer radius in this problem? This is 2 right here. So what's your outer radius? Right x-coordinate is 2 minus left x-coordinate 0. Okay, and that makes sense. The outer radius is always 2, right? And your inner radius, little r, is right x-coordinate, which is 2, minus your left x-coordinate, which is what? This was the line y, or the curve y equals x squared, so the x would be square root of y. Positive, because it's the right half. So this will be 2 minus square root of y. So there's the little radius. Again, right minus left. So what's my integral? Well, the strips, again, same thing as last week. Strips fill the space from 0 to 4. I'm going to pull that pi around on the, out to the outside. Again, what am I doing? Over here on the board, I'm doing area of the slice. So I'm doing the area of the ring. That's at pi times big R squared minus little r squared. That's this part. The dx is the thickness. Area times thickness gives me volume. The integral adds up all the slices. So what do I got? I got big R squared minus little r. And so that's where it can get a little confusing. So it's nice to have written out big R and little r. You don't have to. I'm not going to grade that necessarily. But I think it's a good idea. Type that in. Try that on your calculator. Type that in and see what we get. That would be the area of that solid. So you can take the same region like we did in number 9 and just revolve it around something different and get a totally different solid with, of course, a totally different volume. Matter of fact, one of your homework problems takes a region and the problem is 4 parts because it revolves it around something different every time. Okay? So you probably should draw even a new picture with each one. You'll definitely have a new integral. What do you get? How much? 40 pi over 3? 40 pi over 3. Okay? All right. Let's take that same region. No, let's do it better. I'm going to give you I'm going to give you one region, 2 different things to revolve it around, and see how you do. Then you can do it and you can kind of check with each other and see how you're coming. So let's take this region, bounded by y equals x squared, and y equals square root of x. For part A, let's revolve it about x equals 1. And for part B, let's revolve it about y equals -2. Okay? Try that.